Now we're going to see what is the blended Hubble constant. So here's a diagram again. The distance between the Earth to the galaxy, d1, at time equals 0. We divide that into a number of segments of space. Each segment expands over time because of the expansion of space into its final length, and all of these final lengths make up the final length dn. And don't worry about the fact that I don't have the same number of segments down here. I just ran out of space on the paper. Now, we take the time that light was traveling, the time of the expansion of space, and we chop it into segments, and we label those segments 1, 2, 3, and so on up to W, which is the number of segments we've chosen to use. So, in the first segment of time, the length that results from the expansion of space, which I'll just call d2, equals this initial length, d, plus whatever the expansion was. And that equals d plus, so the expansion is the length d times h1, the Hubble constant at this point in time, times time, the number of seconds in this segment, 1, divided by the conversion factor. And then this simplifies to d times 1 plus h1 times t over the conversion factor. Now here's the key point. The Hubble constant can change over time. So when we get to the second segment of time and we want to expand the space again, we can't use h1, we have to use whatever the new Hubble constant was in h2. So that new Hubble constant is h2. So to take the expansion one step further, the new distance d3 equals the previous total d2 plus whatever the new expansion is. And that equals d2 plus the new expansion is d2 times h2 times t over the conversion factor. And rearranging to simplify gives us d2 times 1 plus h2 times t over the conversion factor. Now, since d2 equals this, we can substitute this in for d2, which gives us this equation. d3 equals d times 1 plus h1 t over cf, here, coming down here, times 1 plus h2 t over cf. So that is the final length up here after the second expansion. Now this process will repeat for every expansion all the way down to the wth expansion, however number of units of, or however number of divisions of time we wanted to make. And the formula for the length of this segment at the end of the last slice of time, so the length at the end of the last slice of time is going to be the same as this, just for more slices, so it equals d times 1 plus h1 times time over the conversion factor times 1 plus h2 times time over the conversion factor, and so on for each of these slices of time there we use another component that includes H3, H4, H5, and so on until we get to the last one for W, 1 plus HW times time over the conversion factor. Now the thing that makes this formula so complicated is that each of these Hubble constants is different for each partition or slice of time as it goes along. So we say to ourselves, what if we could find one value for the Hubble constant, which I'm going to call the blended Hubble value, which we could put into this equation in every spot so that the total of the equation when it's all multiplied out is still the same. This would be a way of simplifying this equation so that it's a lot easier to work with. That is where the blended Hubble constant comes from in this work. It's sort of like the average of all these Hubble constants, but because of the shape of this formula, a straight mathematical average of all these H's will not give the right answer if we use that as the blended Hubble constant. So for now, we just note it as the blended Hubble constant, and I'm sure somebody can create a formula that will accurately describe the relationship, but I am not going to do that. And now we can see how the blended Hubble constant will help us, because if we divided the time into slices where each slice was 1 second long, then the number of seconds, or the number of slices we would have, would equal the number of seconds that light was traveling from the galaxy to Earth. So that would be the number of these components in the formula. So if that's the number of components in the formula, we can write the formula this way, that the final distance, dW, equals the initial distance times 1 plus the blended Hubble value times t over the conversion factor, all to the power of the number of seconds in the time that light was traveling. So all to the power of TL.